Well, hello again, Math Man, back again. In our last video segment, we took a look at the utility of derivatives in deriving or equating infinite series to a periodic, or let's say cyclic function when you take its derivatives. For example, the trigonometric function like the cosine will, when you keep taking derivatives, you go from the cosine to the negative sine to the negative cosine to back to the cosine again. If you keep taking first, second, third, fourth derivatives and so on, it's advantageous because for one thing, you're able to isolate the coefficients of an infinite series, and so you can find a polynomial equivalent or an infinite polynomial series that will represent the function. And it was pretty cool. We went through it. We found the infinite series for both the cosine function, the sine function, um, the e to the x, e to the minus x. We could see how when you found the infinite series for e to the x or e to the minus x or the sine or cosine, you can combine those functions so that you have infinite series representations of other functions like the tangent function or the sinh hyperbolic sine function. So there's a lot of utility there. But one of the things, and we haven't really looked at this yet, we haven't looked at integration. We that's the next step in our program as we move along in calculus. We'll be looking at integration. And I was just thinking about infinite series in relationship to this function. Um, Whoops, I didn't turn the camera there. This function, which is the Gaussian curve. Carl Gauss was the first to really delve into the characteristics and the mathematics associated with this particular function, e to the minus x squared. And we can see that as x goes towards minus infinity, um, we approach asymptotically. We approach the x-axis or y equals 0, with this being the y-axis, and this is the x-axis. And the same holds true for positive x. The larger you get the function, the larger you get along the or move along the x-axis, the smaller the function becomes, and it approaches 0. Um, it's only 0 at x equals infinity, and there's really infinity is one of those troublesome things. There's no real infinity. We sometimes think of it or treat it as if it's a determined entity, and that's not so. Basically, because you, in essence, can never terminate the x-axis in progression. You can go on forever writing another number. You have one, two, three, and no matter how large you go, you can always add another number. You can add another digit to it, and keep going on indefinitely. So infinity just represents that condition that you will never attain. You never attain infinity. But it allows us to kind of look at uh, the behavior of things, like for example, if for example we could attain infinity, this function would be zero. Why would you want to create a series, let's say a naught plus a1x plus a2x squared plus a3x to the third plus a4x to the fourth plus blah blah blah. Why would you want to do that? Well, one of the things is that and we hadn't like I said, we haven't advanced to that point yet. But we're looking at differential calculus derivatives, but there is another branch of calculus called integration, and you can kind of think of integration as the inverse or an anti, like you have sine of x, and then you have sine inverse sine of sine x is x. So you can think of it in that terms, in the same light. This is something that we had looked at with other functions. Um, well, when you take a look at a function, a polynomial, let's say a polynomial function, and we have, let's say, some weird thing like this, x, y, and this is some y equals x to the n plus bx to the n minus 1, blah, blah, blah. It doesn't matter what that function is. You can, through integration, x to the n, and this big S that I made represents integration. It's you've seen me use these function this symbol for summation. Let's say n equals 0 to infinity of n, and you have 1, 2, 3, 4, so on. Well, or that those would be plus and plus, 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 and so on. You would this is the Greek letter sigma for sum, and this was derived by Gottfried Leibniz, who was one of the early mathematicians that helped develop calculus. Uh, and we use his notation. This notation says to do the opposite of derivative. And so we call this integration. And integration allows us, and we'll be looking at this in detail, if we look at the function between x1 and x2, and we have a y1 and y2, the area under the curve between those two x's, what is that? Well, you can integrate that function between x1 and x2, and that's the area under the curve defined under those 2 points on the x-axis. So let's we can integrate a lot of different functions, but we can't integrate that function. Now, if we want to know, for example, it's very useful to know because let's say one standard deviation, one sigma, um, let's see, um, this is one standard deviation, and then we have two standard deviations and three standard deviations. And you'll see that the area under the curve is about 95%, or let's say maybe in this case, I think it's 90%. I think it's 30. This is one standard deviation, I think, is about 60 some percent, 66%. I have to look it up. We'll look at it in detail later when we look at this function a little more with a little more scrutiny when we do integration. But anyway, it's helpful to look at the area under this curve, and you want to get like 95 percentiles, and they are going to be three standard deviations, and you want to integrate this so that you can take a look at, let's say, what percentage you covered in your data. And so it's useful to find the area under the curve. The problem is you cannot integrate this function. There's just no way you can integrate that function. There are many functions that you just can't integrate. There's no way to do it. There are many functions, polynomials. There are many trigonometric and other types of functions that you can integrate, but you're not able to integrate the Gaussian function. So how people do it is by finding the infinite series equivalent of this function. And you know what you can do, as we went yesterday, you can go y prime, y double prime, y triple prime, y 2, 4, and you can keep going. This one's a little more complex because you have minus 2x e to the minus x squared equals a1 plus 2a2x plus 3a3x squared plus blah blah blah. And you can see then even though we always end up with an e to the x factor, it becomes increasingly complex. This one would be minus 2 e to the minus x squared minus 2x e to the minus x squared times minus 2x, which is equal to 4. Let's see, 4x squared e to the minus x squared minus 2e to the minus x squared. And then you can factor that out to make it simpler. It takes a lot of work. I've done this integral, and this series, I've developed this series myself. So we have 2 2x squared. Sorry, I can pull out the e to the minus x squared too. All right, so we got 2 e to the minus x squared times 2x squared minus 1. And that will be equal to, that is equal to 2a2. A3 is even more complicated, so it gets more and more complicated because then you take the derivative of this, and then that's equal to 3a 3 times 2 times a3, and whatever this derivative is, and that becomes even more complex because you got to take the derivative of this and then the derivative of that, and it takes a long time, but you can work it out and you can find an infinite series that represents this function. It's just that finding the individual coefficients, A1, 2, A3, A4, and so on, becomes a little more difficult. It's an interesting challenge, and I'm not going to work it out here. But the thing that is nice about this is while e to the minus x squared is not integratable, you can't integrate that function. You can integrate the infinite series because it's a polynomial. You just use the integration rule for polynomials, and then you can integrate the area under the Gaussian curve as modeled by the infinite series, the Taylor series. So you have that benefit. It allows you then to do something that you would otherwise find no way to do. So there are many advantages of finding a polynomial equivalent for some of these functions. I just wanted to explain that. Now, let's take a look at some other aspects of derivatives. So we're going to take a look at some applications. Okay, well, actually, I did work it out. I found it in my notes, and although this is slightly different, I had given an example. I said e to the minus x squared. I had actually worked that out for e to the minus x squared divided by 2, which is really the same function. It's just slightly different shaped, but it's basically the same function. It's the Gaussian curve, and or the bell curve. You often hear that as another means of identifying this function as the bell curve. And I found the infinite series. And if you go to Wikipedia, you may see a name, something like a power density function. That's what this is. This polynomial series. That's what they're talking about when they mention that. So it's the polynomial equivalent for the Gaussian curve, and this you can integrate. Don't worry about the summation sign. You can just think of this as an infinite series that goes on. increasing powers, going up by 2 to the n, and you can integrate that any number of terms that you would like. The more terms that you add, the better your results for your integration. The closer you come to actually what it would be if you were able to integrate that. So this is one of the utilities of being able to find a power series or polynomial for a function, and in this case, a function that you're not going to be able to integrate. So I just wanted to mention that because I think that's an important thing to keep in mind, especially as we move on and we take a look at integration. Because again, like I said, there are more functions that exist than what you can integrate. Most functions are not integratable, if that's what you can, if that's how it's called. And I think it's integratable. I don't know. Okay, now one of the things I wanted to mention is that derivatives and calculus really had their roots in Newton's contemplations on the universe, in particular gravity. And he derived a number of rules or laws that he made through his inquiries and scientific observations. He wrote several world-changing books. Optics is one. I forget the name of the other. Just a second. I'm going to check on that. Principia. It was a groundbreaking book where Newton laid out the laws of motion and the principles of calculus. And being a physicist, I'm embarrassed that I couldn't remember it. That's really a senior moment. But anyway, he also wrote one on optics, and they're all originally written in Latin. That was the language that all natural philosophers, they didn't have physicists or biologists or chemists, anybody who was involved in scientific inquiry using the scientific method was called a natural philosopher. And that's why science degrees, especially when you have an advanced degree, doctorates in physics or biology, or they're called PhDs, Doctor of Philosophy, because of the early association of science with the concept of philosophical thought. And they called the study of nature natural philosophy. So he wasn't a physicist, he was a natural philosopher. But actually, he was a polymath. Newton, his mind was very dynamic and ranged over many different subjects and some quackery, even to some extent. He was really big into alchemy, uh, even though it didn't have any scientific application. And he actually wrote more on religious topics than he did on scientific, although his most of his writings on religion are lost. But any first year student who takes a physics class will learn about Newton's laws. Oops, I'll just leave it. And the first one, which is not very intuitive, is that when you set a an object is set uh, is set into motion, it will travel at constant velocity in a in a straight path. That I can remember, unless um, in a constant velocity forever, in a straight path forever, forever, unless it is acted upon by an external force. Okay, so in other words, if I were out off of the planet Earth and I was very uh, far away from the Earth, so that the Earth's gravitational influence is negligible, if I launched a baseball out, that baseball will move indefinitely in a straight line from the time I release it from my hand forever, unless it's acted upon by an external force. Now, people back in Newton's day were skeptical of that because when you throw a ball and it rolls on the ground, it eventually comes to a stop. The ball never goes forever. People, uh, it just ran counterintuitive to people's ideas of how objects acted, because in our world, objects always come to a rest. In fact, they believe that the rest condition was the natural state of an object, and that it took force to cause it to move. Well, the opposite is actually the truth. And when you roll a ball or throw a ball, and it eventually comes to a stop, it's because friction, an external force of friction, is acted upon the ball and has caused it to stop. In certain cases, it will alter the trajectory of the ball. It won't move in a straight path. Think of a pitcher in the game of baseball. They're able to throw curveballs, which means that the ball, when they release it from their hand, they put a spin on the ball, and the spin creates a friction, which causes a change in the trajectory of the ball's path. So the pitcher's here, the batter is here, and he tries to hit it, but it's moving away from the base. And the spinning of the ball has brings air along with it. It's friction. The ball is spinning, and the surface of the ball causes the air around the surface of the ball to move along with it. And as the ball moves in this direction, the velocity of the air moving over the ball on one side is faster than on the other side. And so V1, V2, and you create a pressure differential on either side of the ball. And if P1 is greater than P2, it's going to push the ball in that direction. And that's what Daniel Bernoulli found. This is called Bernoulli's principle, and that's like I mentioned. There's a book, a fantastic book. I showed it to you before. That's called The Five Equations That Changed the World. It is a fantastic book. And it does, I do have a copy of it here. This is the book. I highly recommend it for everybody. It's not just mathematics for people. There's a lot about the people who derive these mathematics, their personalities, characters, their little biographies involved in this. And it talks about Daniel Bernoulli and Bernoulli's equation. It talks about Einstein, of course. He changed the whole way we looked at the world. And others. It mentions Daniel, let's say Leonard Euler. We had talked about Euler earlier, Euler's identity. But we got Isaac Newton. We have Daniel Bernoulli and the hydraulic, his Bernoulli's principles and his contributions to hydrodynamics. Michael Faraday, who had no formal education whatsoever, yet he was so much of a genius that he headed up the Royal Lab in England. Uh, did mostly work in areas of electronics. That's why so many electrical um, phenomena are named. In fact, I think there is a unit of measure called the Faraday. Um, and then there's somebody here that most people, maybe chemists, would know, but most people would not be familiar with Rudolf Clausius and the second law of thermodynamics, and finally Albert Einstein and his theory of special relativity. They don't go into general relativity, but special relativity, and that actually is something that's pretty cool. We could take a look at that's something that we can use right now because all it takes is a little trigonometry. But back to Newton's laws. Okay, so we talked about Newton's first law, and there's really no mathematics behind it. It's a conceptual law. The second one is Newton's law of motion. We call F equals ma. This is the second law. And this is force acting on some object is equal to the mass of the object times the acceleration. So this is mass. Let's write this here. This is force equals mass times the acceleration imposed on acceleration. Acceleration. Don't try to spell while you're talking. Um, that's what this F equals ma. That's that for first year students in physics. That's the equation that gets drummed into you over and over and over and over again. And then there's Newton's last law, the third law, which is for every action an object experiences, there's an equal and opposite reaction. So what that's saying basically is if I have a 20-pound ball in my hand made of dense, heavy rubber, and I'm floating in space with nothing to grab, and I've got this ball, and I throw that ball with a certain effort, a certain force, that ball is going to go off into this direction at a constant speed, um, and it's going to have a certain uh, MV. Okay, geez, I'm gonna have to erase all that. It's going to go off with a certain momentum, MV, and I'm going to be moving off in that direction. As the ball goes that way, I'm going to be moving in the opposite direction with an equal M1 V1, M2 V2. I'm going to be moving off with an equal momentum. And so in this case, M1 V1 of the ball will equal my momentum, M2 V2. Now, because my mass will be bigger than the mass of the ball that I threw, I won't be moving quite with the same velocity. The ball will be moving faster, but I will be moving at a slower velocity because of the greater mass. But when you equate the two, it will be the same. So the ball's momentum in one direction when I release it will be equal to the motion that I experience in the exact opposite direction after I throw it. And so that's Newton's third law. For every action, there's an equal and opposite reaction. That's why a gun gives a kickback. When you put a gun to your shoulder and you pull the trigger and fire the bullet goes shooting out. It's a very small object and it goes out at a very high velocity. But because you had quite a bit of charge in there and there was a lot of force imparted to the bullet, you feel a kick in your shoulder, a recoil, and that recoil is the equal and opposite reaction that you're feeling for the bullet that's moving off in the direction you shoot it in. Okay, so let's take a closer look at the second law of motion, F equals ma. And it turns out that these tend to be derivatives. Okay, acceleration is the derivative of velocity over time, dv dt. And velocity, velocity is equal to the change in x over the change in time. where x equals vt, and so v equals x over t, and so dv dt equals dt of x over t. But what I'm trying to arrive at is how we end up with this. We have force equals m equals dv dt, but dv dt, m equals d dt of v, and v equals dx dt. So we have m equals d dt of dx dt, and this equals m d squared x over dt squared. And later on, when we look at integration, we're going to find these relationships very, very useful. So one thing that we should be aware of, we have looked at some interpretations of derivatives. If we have a function, okay, a function f f of x equals, let's say, some a x to the n plus b x to the n minus 1 plus c, something like that. The derivative of x df dx is equal to d dx of a and x to the n plus b x to the n minus 1 plus c, and that's going to be equal to a n x to the n minus 1 plus b n minus 1 x to the n minus 2, and the derivative of a constant is 0. So df dx, that's the first derivative, and that is the velocity of the function. The first derivative is the velocity. First derivative is velocity. And now, if we take a second derivative, dx of df dx, this is the rate of change of the function at any given point along the function. And the second derivative is a n to the n minus 1 x to the n minus 2 plus b n minus 1 times n minus 2. Well, I didn't give myself much room, did I? Let's move it over just a little bit. dx of df dx is equal, in this case, to a n times n minus 1 x to the n minus 2 plus b times n minus 1 times n minus 2 x to the n minus 3. This second derivative, which can be written like this, d squared x dx df d squared f dx squared is equal to this. This is the second derivative. Second derivative. That's not very clear. Oh, boy, this pen. Second derivative. And that's the rate of change of the functions velocity. This is the acceleration. So we have the first derivative is the velocity of the function. The second derivative is the acceleration. For example, if we had a function, okay, and this is true for all things. This is a very important concept. Let's say we have y equals 2x squared plus 4x plus 3. Okay, let's say we can plot this thing on an xy curve. We can see, for one thing, everything is positive, so it will never cross the x-axis into the negative realm. So we can, and we know that because we got x squared, it's going to dominate. So it's going to go up steeply on the left side and on the right side, or negative side and positive side. This is the x-axis, and we got 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3, 0. And when x is 0, y is 1, 2, 3, right there. When x is 1, we got 2 plus 4 plus 3, and that happens to be 7, 8, 9. So when we're 1, 2, 3, We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're up here somewhere. When we're at -1, we have 2 minus 4 plus 3. So that's 5 minus 4. We're at 1. Okay, and then at -2, we got 4 times 2 is 8, minus 2 times 4 is -8, plus 3. So we're back up to here again. We could use our y prime and so on for the minimums. Y prime equals 4x plus 4, and y double prime equals 4, a constant. And so when this is 0, when that is 0, this means we have no inflection points. This function here can't be 0. It's always 4. So it's a constant, and there are no inflection points. Inflection points only occur when you can set the second derivative to 0. So what we have here, this is positive and will always be positive, so it's cup-shaped. We have x, 4x equals 0, 4x equals 0, so 4x equals -4, x equals -1. So there is an extrema at x equals -1, and it happens to be the value 1 at -1. So this is the minimum, the absolute minimum, and this thing curves up steeply like that. This curves up like that. It's a parabola, and it's off center. And what this says, now we know that it helped us graph this awful piece of art that I put up here, but I'm not very good at drawing. My motor control isn't so good. This is the rate of change. Now we see the rate of change of this is not the same. As we move along the x direction, the rate of change slows, or either increases or slows down. But the function actually eventually it becomes the velocity here becomes slower. This is the rate of change of the function at any given point. So that's the slope of the function. And the slope of the function, from left to right, is negative in certain places. That means that this becomes less and less steep and flattens out to 0 and then begins to increase. So the slopes, or the rate of change of the function along the curve, here is negative, so it's decreasing. When it's very far in the negative direction, it's decreasing very rapidly. But as it approaches the minimum, the rate of change tends to slow down and stop, and actually changes, becomes positive and increases. So that's why we got this parabolic curve or cup, sort of like this. And that's a better picture than this thing. And we have, in our case here, it was off center and it's above. It never reaches 0. And this goes up, and this is our minimum at -1. And you can see that the slope is negative here, and it goes downwards, but tends to level off, then stops at this minimum, and reverses and becomes steeper and steeper and growing more rapidly as we move in the positive x direction. So that's what this is telling us. So this is the velocity or the rate of change of the function. That's a general rate of change, but we can find the rate of change, let's say, at x equals 9. So x equals 9, the rate of change would be 4 times 9 plus 4, which is 36, plus 4, which is a slope of 40. So for every change, let's say the dy dx, which we said was the slope, equals m. Well, at that point where, let's say this is 9, we got a very, very steep slope at that point. Okay, but it's not constant. The slope is continually changing, and every point up, it's different. The slope is never the same at any 2 points. And so that's what this tells us, and the function's increasing at a changing in a changing way, depending where you are on the curve. Now, the acceleration, that's what this is. This is the rate of change of the velocity, and that's the acceleration. That's a constant. So the rate of change of velocity doesn't change. It's a positive, and it's above 0. But the rate of change of the velocity is always the same. So while the velocity itself changes, instantaneous rate of change of the velocity or the slope of the curve changes at every given point. The rate at which the rate of change or the rate at which that slope changes is constant and is 4 for this particular function. So we have different ways of thinking now of what the function means. First, it can help us plot the function. And then secondly, it gives us the behavioral characteristics of the function. And that's Newton's laws took advantage of the of calculus of derivatives to help us give a mathematical representation of the laws of motion, the second law of motion, F equals ma. So why don't we take a quick look at the projectile motion. And projectile motion is when you my hand drawing is just awful. I'm not very good at that. Let's see. let's take a look at, let's say, a cannon. All right. Napoleon was great at this. Napoleon excelled in mathematics in school and was very good at projectile motion. And so he ended up in the army, the French army, as a captain of the cannonade because he could. It's important for the cannons to know whether or not they're going to be able to reach their target. So we have projectile motion. So we shoot our object, let's say a rocket or a cannonball, up in the air, and it goes up and it curves down because of gravity and hits the ground at some point x. We're going to say x1 along the x-axis. And this is the y-axis. The cannonball is going to reach a maximum height at some point and then begin to drop back down to the ground. You can do this with a baseball or any other object that you throw. But this is the way objects move under a gravitational field and under what we call 1g, an acceleration of 1g. And 1g, I'm going to do it in English units, is given by 32 feet per second squared. That's the acceleration. So that's the gravitational influence that the cannonball is going to feel, and it's also negative because it's in a negative direction, always pointing towards the earth, always pointing to the ground. Now, when they first shoot the cannon, it's at an initial angle. And once the force has been imparted, the explosion inside the cannon, the ignition of the charge, the powder, imparts a force on the cannonball. And once it's a momentary force, and it's great, and the ball is forced out of the nozzle of the cannon and into the air, and it follows a trajectory on its own. And so once it leaves the muzzle of the cannon, there's no more force other than gravity acting on it, and it comes out at a what we call muzzle velocity. Now let's make believe that we brought the cannon with us to the moon, and there's no air on the moon. There's no friction from the air on the cannonball. So friction will slow it down, and friction is proportional to the velocity when we talk about projectile motion. I think it's proportional, inversely proportional, or let's say directly proportional to the square of the velocity, and it acts in a negative way. So the projectile motion is something that can only be approximated on Earth because we've got an atmosphere. But on the moon, what I show you is going to follow these laws exactly. And space astronauts sneaked golf clubs up on the moon and drove a golf ball, and it went for literally for miles because there was no friction, no air, no friction on the golf ball. So we're going to look at this kind of motion. And we have two components of this motion. We have an x component and we have a y component, and we have two equations that describe that. So when we shoot the particle in one direction, we have several aspects. We have the angle that we shot it at. We have the velocity, the initial velocity. We're going to say, we'll call it V. Boy, this thing's running out. V naught. And we have the angle. And this thing is going to go in some kind of an arc like that. And the distance, x, x is given by the initial velocity times the cosine of the angle times the time of the time in which the object traversed the distance. And then we have a y component where we have v0 times sine of the angle, theta, t, minus. Now this is where the gravitational influence comes in, because it just doesn't keep going up and up and up. It curves back down again. So minus 1/2 gt squared. And those are what we call parametric equations of motion. So we want to know where in these curves where their extrema are. So we want to know that how far it's gone, how high it's gone, and we're going to look at also the time in which the object is making its traverse through space. So let's take a look at these equations and see. I want to take a look at my notes real quickly. And okay, I just wanted to check with my notes real quickly. So basically, some of the questions that we want to know are how long we can expect this object, whether it's a cannonball or a baseball or let's say a bullet from a gun or whatever. I just wanted to write that more clearly. G, the gravitational constant. Oh boy. G equals, that's okay. G equals 9.8 meters per second squared, and G also equals 32 feet per second squared. So given, depending on how the problem is given, those are the two different gravitational constants. That's the acceleration, and it's a constant acceleration. So what do we do? One thing we can do is we can look at where y is the maximum. And where y is the maximum is halfway through the trajectory. Okay, so y is the maximum at x on 2, and due to the symmetry of this problem. And so if we say that y prime, the derivative y prime equals v0, or let's say dy dt is equal to v naught sine theta minus 2 times 1/2, so it's minus gt. And if we set this to 0, equals to 0, we have then figured out the time for the maximum height, which is at x equals 2. So t equals, so we got minus gt equals minus v naught sine theta, and t then equals v naught sine theta on g. And that is the time it takes to get to the maximum. Now, for the whole trajectory, the time it takes to get to x is going to be twice that amount. So we could say time to y max, time to, let's write this, time to y max equals v0 sine theta on g, and time total for the whole trajectory is 2 times v0 sine theta on g. And that's what we plug in here to get the distance, x. So x, the cannonball, is going to go, x will be, when we plug this in there, we're going to have 2 v naught squared sine theta cos theta, okay, over g. But this, we can use our trigonometric identity, and that is equal to v naught squared sine of 2 theta over g. And so that's the maximum distance. So that tells us that's x max. That's where it's going to land. Now we can plug in this time it takes to get to the maximum height into the function, and we can find the maximum height that the cannonball goes. So y max is equal to, now we got to plug this in there, t equals that, so we got v naught sine theta, and that's going to be squared over g minus 1/2 g times v naught squared sine squared theta over g squared. Now, this can be further simplified. So y max is going to be, now that cancels there. We're going to have v naught squared sine squared theta on 2g. That's y max. And so this is our solution to how high the cannonball will go. That's h, or y max. And this is the distance x. Now, all we need now is the initial muzzle velocity and the angle at which this cannon was pointed. If we want to maximize the distance, we can take the derivative of x and set that to 0. And then we can take a look at the angle that will maximize our distance. And I believe when you do that, you're going to find that theta is going to be equal to 45 degrees, or what is that, pi on 4. So that will be the angle that maximizes this trajectory. I'm going to cut it off at this point, but we'll take a look at this one more time. I think we can look at specific problems that are real world problems. Again, these equations all come out of Newton's second law, and we can use them to help us understand how objects are going to go. Now, if we impart enough velocity, the distance this goes will be further and further. So we could have, depending on how much velocity we impart to the cannon, we can start it there and have a small charge, and this is x1. We have more of a charge. We have x2, more of a charge, x3, and so on. Actually, these don't go up that steep. The angles are always the same. I didn't do a very good job drawing that. Okay. So let's say this is x1, this is x2, this is x3, this is x4, and so on. And if you impart enough velocity, x1, x2, x3, x4, and v naught, and this is where we start. If we impart enough, um, because the Earth is curved, we end up falling over the curve of the Earth, and so as the trajectory uh, goes, it never lands. It ends up um, orbiting the Earth, and basically, an orbit is a free fall over the edge of the Earth. It never hits the Earth. It falls over the horizon of the Earth, and so I think it takes a rocket about 17,000 miles an hour to attain that condition where they're in orbit around the Earth. And because there's very little atmosphere or no atmosphere in space 200 miles above the Earth, there's no friction, so the rockets don't slow down and they will stay in orbit for a long time. And that's part of the problems that we have right now is that there's so much space junk that's in orbit around the Earth. It creates a hazard or a risk or danger for the astronauts that go up there because let's say they're in the crosshairs of they're in a orbit around the equator of the Earth, and they have a piece of space junk that's moving in an orbit over the poles. And it just so happens that it hits their spacecraft. They will be hit by a particle that's moving 17,000 miles an hour. Bullets, as fast as a bullet comes out of a rifle, a powerful rifle, it's still nowhere near the velocity of an object in orbit around the Earth. I mean, 17,000 miles an hour is a tremendous, um, a tremendous velocity and very, very dangerous. Even small objects moving that fast, let's say a nut or bolt or just a scrap of a metal, small piece of metal, moving at 17,000 miles an hour will go all the way through a human being, and will it could compromise the tiles, the protective tiles of the spaceship, or penetrate the windows. That's why they make the windows of these spacecrafts of very very thick glass, so that there's little chance of a particle um, compromising and cracking the glass such that it poses a danger to the astronauts. So anyway, we looked at a couple of things. We looked at some applications of derivatives, and we looked at projectile motion. We looked at the concept of the first derivative being a uh, representing a velocity, the rate of change of the function over time. And the second derivative is the rate of change of the velocity over time. Or whatever parameter you're measuring. Let's say it's a function of x. Um, the first derivative of, let's say, a polynomial is the rate of change of that polynomial when you trace its curve on a Cartesian coordinate system. Then acceleration is representative of the rate of change of the velocity, and that can happen when curves move around. Let's take a look at this, and when curves, um, the curve we looked at was just a parabola, like that. So there was no, it was the second derivative, y double prime was constant. And so it was positive. It was positive, so it was cup-shaped. And therefore, it didn't change the shape of the curve. It's a but we had y prime as being a function of x, and it was a first order function. It was 4x plus 4, and so the slope changes instantaneously around the curve, but it doesn't change its shape. In other words, it doesn't go like that. It just continues to go in that one direction. So where we have a function that, like we had in our last video, where a function goes like this, like that. It's not perfect, but you get the idea. It goes up like that, it goes up like that, and there was symmetry through the y-axis, and this was x0, this was 1, this was minus 1, and here we had inflection points there, and there, whoops, and there, which means that darn it, this thing's starting to boy, it's certainly not working very well. Okay, our inflection point was right in there. Well, and so you could see that the curve changed, and we had a maximum, a local maximum, and we had local, this thing stopped writing, local minimums, and so we had a function that was y. Boy, this is dead. I just killed it. There we go. It seems like if it sits a while, I can draw some life out of them. So that's a max and min. This is the curve. This is the inflection points. And y equals, it was some function that was x to the fourth plus some constant times x squared plus d. And then y prime was a function, a third power, third order function, and then y double prime was a second order function, which means that we had two inflection points. In fact, what that means is that that the acceleration or the rate of change of the velocity along the curve changed. And so that's where we get an inflection point, is where that velocity changes. And we had the rate of change of the function, which is the velocity or the rate of change at which the slope along the curve changes as a third order function. So anyway, those are some of the properties that we have. First derivative is a velocity. The second derivative is acceleration. When you set these to 0, they allow you to understand characteristics of the curve, where the maximums are, where the minimums are. And so there's a lot of utility to derivatives. Plus, we were able to um, use them to find polynomial equivalents for certain functions that we realize are going to be helpful to us, especially in the future when we get into integration, being able to convert a function that's not where you're not able to integrate it, like a, uh, um, a Gaussian curve, a Gaussian function, which cannot be integrated, but you can convert it into a polynomial, an infinite polynomial series, and you can integrate that series and and obtain the areas under the curve that you're interested in. So anyway, I think we're almost played out with derivatives. Um, there are functions that are more complicated that are of multiple variables, x and y, f of x and y, and you can take derivatives of the function with respect to the x or derivatives with respect to the y. They're called partial derivatives. We could take a look at some of those before we leave the topic of derivatives. We'll maybe take a look at that and briefly, and I'll take a look at the possibility of more examples of where derivatives are useful to us. So anyway, this is Mathman wishing you well and wish the best. Stay safe, and we'll see you again soon.